Thank you very much. I don't know if we really need a microphone here. Do you want to use one or you prefer with that?
I don't think it's necessary.
Well, there's video recording going on, so
Is it necessary for the video to use a mic? Okay.
yeah.
Hello. My multi-purpose jacket.
Anyway, so let's start the scientific part of the workshop this morning. We have 4 half-hour talks, all from people from Oxford. And the first one will be given by Bob. Please go ahead.
Okay. Okay, thank you everybody. This is going to be a very short talk. Just a short result, these things happen. And since there's no way I could otherwise fill half an hour, so I'll do a brief intro about this paper. But the main reference of the start is this. Alright. So the title says terminality environmental signaling. So it has to do with causality. And the problem with causality is like if you look into the literature, well not just the literature, but just some culture, then causality is used in a lot of different places in many different ways. So probably what I think most people understand by causality is the idea of space-time reachability concept. It's really space-time, whatever you can reach, whatever light can reach. So that defines partial order. Light can get from here to some point in the future, which means this point is in the past at that point, and then you say this point is less or equal at that point, and what you get is partial order. And that's something which was already a long time ago identified by Penrose as sort of the first level, the most fundamental level of causal structures as in relativity theory. So it's partial order. But you find actually exactly the same type of partial order in computer science. Well, they use causality as like which events actually cause which other events happen. So people are now, this is actually a very active area of research as well. This guy got a Turing Award 2 years ago, 1 year ago, I can't remember. So okay, so these notions of causality, although one is from relativity, the other one is from computer science, that's pretty much the same thing. So it's this reachability. Another thing which you see a lot in common foundations, it's the idea of non-signaling, tries to implement this idea for like devices, for operational devices, which typically involve two inputs, two outputs, referred to as Alice and Bob, and then doing some information processing tasks. The idea is then to understand things like quantum non-locality better. It's like you've got a certain device, you've got one input, you can write it down, it's going to be worth, you've got this picture in your head at the moment already. So you've got a device, here you've got Alice, and then you've got Bob. They each have an input and an output. And then the idea is that in order to be compatible with the first thing, it should not be possible for Alice to communicate with Bob, supposed to these devices spread out in space. Right? And the formal way to think about this, I'll talk a bit more later. I'll talk a bit more about that later. Is that if Alice puts an input here, then it should not be possible for Bob, from the pair consisting of his input and his output, deduce anything about Alice's input. Because otherwise it would violate relativity and communication faster than light. So, okay, here, this is the second notion, of causality. And then there's a third place where causality actually appears, and that's actually in papers by Giulio and Mauro Daiano and Paolo Cornuti, and they have like an axiom which they sort of motivate as no signaling from the future. No signaling from the future. So not non-signaling, but non-signaling from the future. Like if they want measurement, then the outcome shouldn't affect something in the past. So this sort of clearly seems to indicate that these two notions are different. You would hope that these notions are more or less compatible. It doesn't really turn out to be the case. And that's pretty much what this second paper here was about. So I'll quickly say what was in there. So here is this causal structure coming from relativity or from Pearl-style causality reasoning. a property of a causal structure is that it meets the notion of time reversal in the sense that if for t, like the normal flow of time, you got an event A, which is in the causal past of an event B, then for the reverse time, B will be the causal past of A. Pretty obvious. Huh? If you reverse time, whatever is in the past will then be in the future. And more importantly, if two things are causally non-related, so if A is probably not in the causal path of B and B is also not in the causal path of A, say, then if you reverse time, they still will be separate. They won't suddenly become causally related just by flipping the direction of time. And then the thing Ray and I observed is that this obvious structural property of causality as in the causal structure is actually not the case anymore for non-signaling, as I was describing it there, which basically means there I wrote down this box like one input, one output, one input from Alice, one output for Alice, one input from Bob, one output from Bob. Suppose now that we flip this upside down, like the future, the past becomes the future and the future becomes the past. The outputs become inputs and the inputs become outputs. Well, I'll write an example of something like so. What you can write down is, for example, a matrix saying which input pairs relate to which output pairs. Like if Alice gives this input and Bob gives this input, what are the possible outputs that could come out from that? It's a question you can ask. And then basically time reversal would mean take the transpose of this matrix. Because if something here, if a pair here relates to a pair there, then backward you would say that pair can relate to a pair here. It's like the relational converse gives you flip. Now you can do the same by instead of considering relations, considering probabilities, of course, in which this pair relates with a certain value to that pair, and then you would do something like Bayesian inversion to time reverse. Well, I'm saying this is obvious, but let's talk about it later. But anyway, so this is a relation which has an underlying probability model which is classical. There's nothing quantum about it. It's classical probability theory. You can build something like that with classical probability. This particular example. However, if you do the time reverse of this one, you get a signaling box. So something which forward in time is a perfectly classical device which you can build in a factory. Backward it becomes a signaling device which violates relativity, which is kind of weird. Okay, so the point is not to look into details in this, but like for this particular device, it is just how you do it. If Bob would input the 0, then his output is exactly Alice's input, so you get a perfect signaling channel. So if Bob keeps on fixing in the time reverse on input 0, then you get a signal. So what's wrong here? What's wrong? Clearly seems to indicate a mismatch between these two notions of causality. That one has this perfect, this nice symmetry that it meets the notion of time reversal, and the other one doesn't really have that. How come? So that was sort of one of the things which puzzled me for a long time. What's wrong there? Something must be wrong with this whole argument. You can in the paper we described like an operational way to realize this idea of time reversal, and then because we want to get this in TRL, we said we discovered a new error of time, or something like that. Otherwise you can't get in there, or something like that. The way you want to think about this is like you got some device, and it has a slot, and you put something in this slot, maybe a card or something, and then you get something out of that slot. So if you would videotape, and you would reverse the videotape, it's sort of a symmetric action. So you wouldn't really see from the action which is taking place, because somebody's sticking something in and something getting something out. So if you reverse the tape from the direction of the tape, you wouldn't really see was this a forward direction or the backward direction. So you build this device, this perfect, you build this device, which I described on the previous slide. You build this device, two people are operating it, and then if you reverse the videotape and you start computing the statistics, then actually you see that they're actually signaling, despite the fact that they may actually be in spatially separate RS5 parts. So you can actually detect from the video whether you're playing it forward or backward. So it's like an error of time. So you can detect whether the time is flowing forward or backward. So it's of course bullshit. But there's something wrong here. There's something wrong here. But on the other hand, what I'm describing is perfectly consistent with this type of. And for me, the main result about what I'm going to talk about is actually understanding what's wrong here. So what is sort of conceptual flaw here? Anyway, so what we will try to do is to show how these things are related. So we got this structure space already, we got the signaling, and then the causality option, which is non-signaling from the future. Now, all these things are called causality in a way, so I'm not going to call this causality anymore. Otherwise it would be too confusing. Okay, so the language we are going to use is just like boxes and wires. So, like probably every paper I've written in the last 10 years is about this. Like you got devices, here you got a device to inputs to outputs, here you got a similar thing, and the wires just represent communication of data. Propaganda, electricity engineer, and I are about to finish a book hopefully next month about, which is called Quantum Theory in Terms of Diagrams, so you can buy that if you want to, if it's finished. For people who like symbolic mathematics, this thing is a symmetric strict monodic category. That's what we're working with. So we work with any symmetric strict monodic category. We think of this as a theory of processes. It's very general. So what we call a state is a process without an input. What we call an effect is a process without an output. And a special effect, and the only one we really assume is called discarding. It means throwing stuff away. Discarding is throwing stuff away. So you can have many other things in your theory, but that's the only one we will assume that is always around. It's operationally justified. It's like not taking account of something, forgetting something, destroying something, all that stuff is simple. Okay, terminality is actually what I'm going to use as name for what Giulio and his collaborators called the causality axiom. It's basically this picture. So we say that a theory, a process theory, obeys terminality or blah blah blah. If for every process, if you throw away the output, then you could throw away the output from the start anyway. Or then you throw away the thing you take as the input. It seems like a very reasonable assumption in many theories. Right? So you have to assume that these things have no other inputs and outputs. So whatever I draw here, it's one input and one output, and there's nothing else. Because if there would be other wires, then you wouldn't assume this to be true. But if there is no other wires anywhere, and this thing is just in isolation there, and you're going to throw away the output. It's like you run a computer programming, and then you don't read the output, and you just destroy the computer. Well, you could as well have not run it, you know. That's basically what this is saying. So it's a very reasonable assumption, you could say. And then what you can show is that this notion of terminality is equivalent to that all effects are actually this one. Why? An effect is something without an output. So take away, if it has no output, you don't have to throw the output away. So here you've got your effect, and it has to be equal to that. So all effects actually have to be of this form. It follows from this action. And then it also immediately follows that there is actually only one effect, which is that guy, throwing away. Which also, for example, implies then that if I've got throwing away of two systems, then it has to be this. Because the tensor of these things, of course, exists because we have a monoidal category, and we can just, so the one throwing away two things is the same as throwing away each thing. Obvious. Okay, that's equivalent. And so the name comes, of course, because all of this means that the tensor unit is thermal in category. That's what it means. That's where the name comes from. And it, yeah, I don't care about loop space. This would be CPM field, for example. And normalized. Everything, like here. This terminology means normalization of probabilities and states, which would mean that you only have one scalar. You can only have one scalar. Probably you could use classical probability distributions and stochastic maps. So examples are probabilities, which are normalized, states, which are normalized, trace preserving stuff, like for completely positive maps. It's what everybody does when they compute. Everybody does that. Yeah. The Hilbert space doesn't obey it. Quantum mechanics has nothing to do with Hilbert space directly. There's something to do with something you derive from Hilbert space. But it's not about linear Hilbert space or linear maps. Like the fact that in quantum mechanics, like your projectors or your positive, your POVMs follow like our resolutions of the identity. So you had a lot of that's all under this. This is all is comprised in this kind of action. It's everything which has to do with normalization. So that's what this action tells you. So it's something everybody does, but never sort of thinks of as an axiom, really. Okay, now we want to formulate this thing of non-signaling. I kind of explained it already there, how it works. So non-signaling basically means, so this is non-signaling from Bob's perspective. Like, so from Bob's perspective, what you should actually assert is that this input never reaches its input-output pair. Which basically means you'll never have access to Alice's output, right? So you can trace away Alice's output, and what we want is actually that this factors in this, so that from Bob's perspective, what he has is an input-output box without any sort of effect from Alice's input. Right, that's kind of what Bob sees in the non-signaling theory. That's what he sees. So this is like the non-signaling from Alice to Bob for this particular process. Now, it's a bit harder to say what it means for a theory to be non-signaling. Anyway, this is from Bob to Alice. It's a bit hard to say that the theory is non-signaling. Why? Because in every, I said we start with a symmetric strict monodal category or something like that, so you got stuff like that. And in a process theory, it's perfectly okay to sort of have two inputs and then swap them, or it's sort of, you do of course a lot, this rewiring sort of stuff. But it's of course, if you analyze this from the perspective of, say, this definition, or just intuitively, yeah, obviously this is signaling from Alice to Bob, because it's a channel from Alice to Bob, so it's signaling. But, so how would you say now that theory is not signaling? Well, you don't want to consider these guys in your definition of signaling, right? And basically what this assumes is that you want your signaling non-signaling constraint only to apply to causal situations where Alice and Bob are far apart. And there cannot be a channel between them. That's how you restrict things. So you want to consider internal causal structure. You want to see what's happening inside this box. Like, you want to make sure that if there is no signaling channel explicitly from Alice to Bob, then they should be able to signal. That's pretty much what you want to say. Now, what is with little bit, so you can then start to see what is the sort of all possible internal causal structures that you can have, and it's pretty much this. So here, this is Alice's input-output action, Bob's input-output action. They may share some resources in the past, they may share some resources in the future, but nothing can go between them. And actually, the only causal structure you get is like a diamond type of thing, like this. Because if you get all the stuff which is in the future, you can sort of put together here, all the stuff which is in the past, you can put together here, and then maybe the other stuff which only affects Alice, other stuff which only affects Bob, you put this all together here. And you probably can easily generalize this idea for 2, 3, 4, 5 parties, whatever. Like what is the simplest, most general causal structure for which there is no direct channel between Alice and Bob? And this is this. And now we can sort of define a non-signaling theory as something in which all these processes are non-signaling. That's what you. So it's a much more involved definition if you want to do it carefully. But this is like sort of this is the definition of non-signaling in a process theory. It's not so simple, but it's as simple as you can do it. The main result is, firstly, that this notion of normalization, terminality, causality action, whatever you call it, implies non-signaling. Always. So how do you prove that? So this is like a special case of this terminality where we have two inputs and two outputs. Huh? Like if you throw away everything at the end, you can throw away everything at the beginning. Okay, let's see what this means for this. First of all, you already see that there is a double effect. So automatically this goes away. Right, this action, automatically this goes away. So that's trivial. So the future, and that's why everybody always starts. So this is the sort of thing you find when people are talking about Bell inequalities. You got some resource in the past, Alice does something, Bob does something. But bigger you see, but implicitly there's already no normalization assumption to go to this setup. People just do it, but it's already there. Now, this was definition of non-signaling. So now we have to see what is if. So we throw away L as output. What do we get here? Up. So this result, which this goes away, up, we're done. Right? Because the definition was there exists an age such that distinct factors in discarding and an input-output box. That's what we get here, yeah?
So the processes in the definition of the signal theory are those processes that are non-signaling.
So the definition of non-signaling, let me go back, is it means everything of this form is non-signaling.
So FA and FB inside this diagram have the other property that you have the other side.
Non-signaling theories take any symmetric signal or category, take any theory of boxes and wires, if everything of this form obeys this, obeys this non-signaling condition, which is this, that is non-signaling. Yes, this is stating non-signaling. It's much more complicated than the other one, obviously, but it's the simplest you can actually formalize. You never see this in any paper. Nobody does it. It's all implicit. These causal assumptions are implicit. Okay. So I would say this is the main result, that this terminology implies non-signaling. Actually, they are equivalent, it turns out. What the other implies one, two. And yes. So, and the way to see this is simply you take your second system trivial in this equation, and then you get the other equation. And so the only thing, then you have to do actually one more assumption that there is only one scale. You have to assume this here. Because otherwise this thing doesn't vanish. So the main result is like these two things actually are equivalent for a very general class of process theory. You don't have to talk about probabilities, you don't have to talk about anything. Because usually these things are defined in the context of probability theory. You don't even have to talk about probabilities. It's something very much more primitive, these equivalents. But of course, so non-signaling requires causality to even be meaningful. To even be meaningful. People don't do this in the papers. They don't do this. Except maybe you. But then it just follows from normalization. People also don't do normalization as an action typically. They just do it. They assume it. Probability. They assume probability, and probabilities are normal, so they assume it. Right? So conceptually, this thing is the causality action from Ovea guys is much simpler. So this should be taken as fundamental, no signaling theories. So the choice of name was right. Yeah. This paper's justification of their name. Good choice, both choice of name. So now to go to amazing. So what about this like weird time reversal box? Like what I would say is, okay, causality can perfectly be time reversed, but if you look at this axiom, which is like a this now, I think this is such a fundamental axiom now. Where is it? Yeah, obviously this is non-time symmetric. So your process theory is manifestly non-time symmetric. This tells you that there is only one effect. So talking about time reversal with respect to this process is just rubbish. But that's probably what went wrong with the previous thing. Now we can do a lot more with so this causality, like the book Alex and I have been writing, we take it as an axiom. We basically take it as the most fundamental axiom. Quantum mechanics is a certain theory of processes subject to this causality axiom. And you derive everything from it. You derive Stein, spring dilation, everything just trivially follows from this axiom. And I just have got one example here of something which follows. So this is some argument we had in this paper, but earlier it was like in the paper by Nakash and Blue that actually traced down back to Fortini stuff. Although again in all their proofs, they didn't kind of realize what they were proving was just a consequence of normalization. They didn't realize it. They were just using normalized stuff, so they never sort of saw normalization as a thing which is doing all the work. And so if you consider a like hypersurface as a follow away, so here you've got some diagram and you can think of it as a causal structure. So here this you could think of as like hypersurfaces, and here you see a foliation, like to evolve from the past if you should do such a diagram. Of course, you can have different foliations, and relativity theory, basic covariance, says that independent of your foliation, you should see the same physical laws. So your state should evolve according to the same physical laws, independent of the sort of foliation you choose, right? But here you can see how such an evolution is. Here you would have a state, and then at a time later, you see it just evolves. But the idea you want to show is that independent of the choice of foliation, this evolution is always the same. So it means independent, because this foliation you have to think of this choice when you're observing, stuff like that. And from causality, this immediately follows. You see, this is equal to this. You see that this is equal. So this state here doesn't depend on the context, just by the, because this is just this terminality action, and so basically covariance, or at least the covariance is just a consequence of that. Yeah, that's it.
Like you sudden reaction. Very good. Let's thank Bob. Any questions? So, Bob.
Okay.
Oh, there was a question.
No time.
Very good. Great. Yes, while you're setting up, maybe you want to find questions?
So doing things in this way allows you a lot of generality that is more than in the probabilistic case.
But probability, like this assumption is partly implicit. It's partly implicit because you use probabilities which are normalized.
Yeah, I was wondering if there is some strange or unexpected application of these things in maybe some different domain of, I don't know, model theories or kind of...
It's very trivial. It's very trivial. It's very trivial as a piece of math. Really trivial. You wouldn't expect to get too much out of it, but you get covariance on it. So I think it's a very good exercise you guys came up with. I never appreciated it that much.
So nothing happened in logics like if you put this...
Possibly, I don't know. I don't know. Could be. Normalization is something people do never think about as doing something structurally. Yeah, but it's very deep structure.
Still another question? Ray, you want to finish it?
Yeah.
A quick one?
Yeah, just wondering. So to define terminality, you already need to know which things are your effects because it's manifested.
So the assumption is that what you have is called a process theory. So you got all your processes. You got your types, which are the wires, and you got your process. That's given. That's your theory.
So you're given a causal structure, and then on top of that, you put like a process theory.
Well,
I'm just
I
wondering.
don't think you need like some causal structure as a separate structure because all the definitions are in terms of colloidal categories. In a way, it's just a certain diagrams obey a certain property.
I guess I'm just wondering if you're trying to do some kind of causal inference where you're just given a bunch of statistics and you don't know which way time is going, and you use something like terminality to try and figure out, which.
That's a good question. That's a good question. That's a good question. Oh, sorry. That's a good question. I don't know. But yeah, could be, probably. I would say yes, because that's actually where the first example went on.
Okay, thanks. Let's continue with this offline. Next speaker is